Here we are. I hope you see me and hear me. Okay, so welcome everybody. I'm Silvano, and today we're gonna go through some linked list exercises. We're gonna go through the C++ simple linked list exercise. Already done it once, but we do it together again. There are some other runs that I did, and here it is. So I want to talk a bit first about linked lists and why they might be necessary, and why I would want to use a linked list instead of, say, an array or something similar. The advantage of linked lists is that you don't need to resize them. They can grow as much as memory you have. Also, they don't need to use memory in the same way as arrays. For example, I'll talk about this more in detail later, but basically you don't need a contiguous amount of memory to store a linked list, to be precise. But let's start with the exercise. This is the scaffold that we have. We have a class list. There's a default constructor. We won't need to build one for it, since just a list. It doesn't have a default constructor. This is important because we'll see to it later. Also, we won't bother about moving and copying for now. Maybe if we have time, we might do it, but it's not really important for the exercise. The important part is this four methods and the structure. The size is the method that returns the size of the linked list, the number of elements that are in it. Push is a method that adds an element to the linked list. Pop pops the first element from the list, and reverses the linked list, making the first element the last and the last the first, and all the others in between. You see, also we have some private members. We have a element struct. This is what is actually gonna hold onto the data. The element just takes as a simple constructor. It stores an integer that must be set when you construct the element, and a next pointer that points either to a null pointer or to a pointer to another element. We'll see why this is necessary. And also we go back to the list. We have we have just two members, private. The add, that is the first element of the list. In this case, it's initialized as a null pointer. An empty list doesn't have an add, doesn't need it. And the current size of the list, the number of elements that are in it. As again, by default, it's 0. And every time we push a new element, we increment the size, and when we pop, we should decrement the current size. That's it. Let's go into the at least this is the definition of the class. Let's go into the implementation. Okay, so I want first maybe to read the instructions and the ints, then we go to the implementations. So the instruction for the exercise are pretty simple. Write a simple linked list implementation that uses elements and a list. The linked list is a fundamental data structure in computer science, often used in the implementation of other data structures. They're pervasive in functional programming languages such as Clojure, Erlang, or Haskell, but far less common in imperative languages such as Ruby or Python. The simplest kind of a linked list is a singly linked list, the one we are implementing right now. Each element in the list contains data and a next field pointing to the next element in the list of elements, as we could have seen in the element next member. The variant of linked list is often this variant of linked lists is often used to represent sequences or push down stacks, also called LIFO stack, last in, first out. Basically, the last element you push in the list is the first that comes out. So when you push an element and then call pop right away, you're gonna remove it right away. As a first take, let's create a singly linked list to contain integers and provide function to reverse a linked list. That is, when implementing this in a language with built-in linked list, implement your own abstract data type. Obviously, C++ is a broad language, so it has an implementation of linked list, but we're gonna do our own in this case as an exercise, obviously. Implementation means we have provided the general structure of a list class for you, as we just went through it. There's the private variables head of type element pointer and current size of type size that you can use. The element struct was given as well. It has two variables, data of type int and next of type element pointer. You can see in the details in simple link list.h as we just saw. You do not have to change that file, but you can you can if it fits your needs. We maybe won't do it for now. Maybe if we have more time, we can go through some other things. The tester use the function that are supplied in the simple linked list CPP. Don't change the signature. You can add more functions and members if you want to. Also, there is this small question. Can I use smart pointers? Although the header file includes raw pointers, you are free to choose a different implementation. Smart pointers are a cool way to handle pointers in C++. They're also much safer to use than pointers, raw pointers, as they're commonly called. These are raw pointers since we're using the asterisk to mark them. And probably we won't do it this time. We won't use smart pointers, but we'll see. Maybe we can give it a try. So let's start implementing our size function. This is really pretty simple. It must return the size of the list, the current size, and that is current size. So we can do it right away. We just do current size, and that's it. We can even remove the to-do. And then we have the push. This is kind of simple method to do. We just need to add a new element into the list. So first thing we do is we check if we actually have an head, because if it's a null pointer, it means that the list is empty. So we just do this new. The head is a new element. We're gonna use the new to create a pointer to the element, and the element class needs an integer called the data that we're gonna store into the element. So we're gonna pass the entry to it, and this is good. Oh, right. And we're gonna return. That's it for the. This is the simplest case when we're creating, we're pushing it to a list that has no elements. There is really nothing else to do, because the element already by default, the next element points to another pointer. So there's nothing else after that one. So that's good. Instead, if we have already an head, we should do another thing. We create our new element, you call it. We're creating an entry. That's it. And we're gonna point the element next. It's gonna be equals to the current head. And then we gotta change the current head to point to the newly built element that we just created. That's element. And that's it. Also, we need to do another important thing because we need to increment the size because we just added a new element. And this is our push method. Let's go through it again. Basically, first thing is first we check if the head exists, if it's a null pointer or not. If it's not, we just go to the next step, and that is creating a new element. That is head. We store it in a temporary function because if we assign it directly to head, we would lose the pointer to the actual head. So we couldn't do this step here. This is really important because if we just do this, we lost. We have dangling pointer, the pointer memory that we cannot access directly, and we cannot point at the newly created element to the previous head, the element that was previously the head. So we gotta do this stuff. And then it's the turn of pop. Pop should do three things. First thing first, we must actually check again if we have some elements. Because if the list is empty, we cannot do anything. This is an error. We already imported the std except header, so we're gonna throw right, I forgot the throw runtime error list is empty. Can't pop anything. That's it. So the list is empty. Throw an error. That's it. Also, another thing that we gotta do after getting the element is return the data that it holds inside. So we're gonna take our element. That's gonna be head. Then we gotta change the head because we need to remove that element from the list. So the new head is gonna be the next element that was the head. And then we know that we gotta do another thing. We're gonna take the data. This is a new variable, so we're gonna call it data. We're gonna take the data from the element that we just removed from the list because we gotta remove it. We gotta return it. And we do this because we gotta delete the element. This is really important. If we don't delete the element and just remove it from the list, this memory is still gonna be allocated. It's still gonna take space in our memory, and nobody has a reference to it. So that becomes a dangling pointer, and that will live as long as the program that we're running is running, and that occupies memory. So it's important that we delete this pointer. And obviously, we must take our data from that element before returning it. We could do it. We could do actually this and return, but that creates a dunking pointer. So we gotta do this step here. So this should be it. Let's go through it again. There is no element. There's nothing in the list. Throw. Perfect. We don't need to return after this because it's just gonna throw an error. The caller of pop must handle this error somehow, and that's up to them how they do it. And there's really nothing to return also. So we get the add. The new add, we also save it. The new add becomes the. Actually, we could maybe. Now we can simplify this. The new add becomes the next element, the second, and we get our data. We delete the element and return the data. Perfect. Maybe we could already run some tests and see what happens. Probably it's gonna fail miserably. Oh, 7 tests already passed. Let's see what happened. Empty list as size 0. This is passed. List as correct size after pop. Okay. List as correct size after pop and push. Let's see which tests are those to be sure that everything is right. So empty list as size 0. That's correct, I guess. This test creates an empty list, asks for its size. The size is 0. Perfect. Singleton list as size 1. So what does this do? This passed. Oh no, this didn't pass. What happened? Oh, we forgot a thing. We didn't do an important stuff during pop. We must decrement the current size because we increment the size in push, decrement the size in pop. That's really important. Let's run the test again. We'll expect some other test to pass. Oh, another fail. What's going on? There's something wrong here. Okay, this creates a list. Okay, pushes an element. Yeah. Oh, see. Yeah, there is an error here because we're not incrementing our current size after creating the first element. We should maybe we have two different solutions here. We can either increment the size as first thing first. Here we increment the size and remove it from here. So we're sure that it's going to be always incremented. Otherwise, we could just go with, we could remove the return here, create a branch in the if here. And then increment the size only after everything has gone through. This is probably better. So let's try. This test now should pass. 9 tests passed. Only one is failing. The reverse not empty list. Yeah, because we still have not implemented our reverse. So yeah, reverse empty list. Oh, reverse empty list is working because we have nothing to reverse, so that works correctly. The reverse non-empty list is not working. And that's correct. We should maybe implement that one. So let's go through the reverse then. What should we do to reverse list? First thing first, we should keep track of the current. We gotta traverse the whole list to reverse it. Otherwise, we cannot point an element to a previous one. And we're gonna do this. We're gonna start from the head, go to take the next element it points to, and make that element the current one, and then point the next of that of the current one to the previous. But first, we gotta also keep track of the next of the next. It sounds a bit complicated. Maybe I didn't explain it that well, but let's go through it. So first thing first, we gotta keep track of the current element, as I said. The current element is a null pointer. That's okay, because we're starting from the first one. We're not sure what we're tracking. So while the add is not a null pointer, so that means it won't work. It won't do anything for an empty list, and that's correct. So we're gonna keep track of we'll have a temp element that we need to move things around. Then we gotta the current becomes the head in this case, because each time we move from an element to another, we're gonna move also the pointer head of the list. So the current becomes the head, and then the head becomes the head next. As I was saying before, we gotta keep track of the current. In this case, it's the head, because the head, the next step becomes the next pointer. So if we didn't do this, current equals head, we'd lose the reference to some elements, and that's bad. So the current one, then the next points to the temporary one. That is the previous one. And we're almost done, because at last we gotta set the head as the current pointer. Because after we traverse the whole list, the current one, that is the last, becomes the head. And this is how you reverse a list, linked list. We go through each element and invert the next to the previous one. So let's run the test again. Cool, they're all passing. There is still an important thing to do, and that is the destructor. As of now, when we push new elements into the list, we're gonna create new pointers. We're gonna allocate new memory, and that memory belongs somehow to the list, and that should be the list job to delete those error memories, to deallocate them. Otherwise, it's gonna fill up all our memory, and that's bad. So let's go through it. Let's remove from here also. It's not necessary anymore. So what we're gonna do in our instructor? We're gonna go through all the elements, same thing that we've done here. While the head is not a null pointer, that means it's not an empty list. We do this. We get the next element, that is the head next, and we delete head. You're gonna say, what? Why? Because when we delete the head, we also do another thing. We change the head to be head next. That's why we say next here, because we're gonna do this. So what is this gonna do? Let's say we have a list of 2 elements. There is a head, and it points to the next one, to the next element. It starts. Okay, head is not a null pointer, so we go through this. We got we save the next pointer, so that is the second one. So we have stored it somewhere. Then we delete the head, and it goes out of the scene, but we still have a pointer to our next element, and we make it the head. So we finish the loop. We go through it again because we still have an head that is not a null pointer. We get the next of the head. It's gonna be a null pointer in this case, but we save it in any case. We delete the head, the current one, that is the last element, throw it in the bin, and we assign next, that is a null pointer, to head. Then what happens? We go through the start again, head is a null pointer, we don't go through the loop again, and that's it. We deallocated all the memory that the list was using. And this is important to do only when destructuring, obviously, when deleting the list. This is really important. This is something that I cannot stress enough. Deallocate your memory. As, for example, we do it here. We delete the element when we pop it. Otherwise, it's gonna be occupying memory forever. Not forever, but at least until the program keeps running. So I want to explain a bit, as I was saying earlier, how the memory is handled by linked list. Imagine that this is our memory. This is a block of free memory. There are things allocated, and just block a bunch of things. We don't care. Those are other programs that are running. Imagine that this is memory. When our program starts, it allocates some memory for it. This is our memory. Okay. Maybe let's do it like this. Then we start allocating some things. We need an array of size 5, let's say. Okay, 1, 2, 3, 4, 5. And we occupy that memory. This is the yellow part is the memory that we have available for our program, and it can grow. It can might not shrink necessarily, but it's free memory we can occupy. Thinking about arrays, we need an array of size 5. An array is important that is that occupies contiguous memory. It cannot be, for example, let's say I need an array of size 5, so I'm gonna oops. I cannot do this. I cannot allocate a memory an array like this. It must be all contiguous memory. 2, 3, 4, 5. This is really important. Similarly, as linked list, an array points to the first element of the area of memory that it occupies. The problem with arrays, and that if we add some data here on the first position, then on the second, then on the third, then on the fourth, then on the fifth, and we fill up our array, we need more memory, and we cannot go and just right there. There might be something else written in here. Let's say this is occupied. What happens? Because the program is doing other stuff at the same time, and this memory is occupied now. What are we gonna do? We're gonna double the size of the array, that was 5. And as I was saying, it must be contiguous memory. So I'm gonna occupy first 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 area of memories, and copy over the stuff that I had in the previous area of memory to the new area and delete the previous one, meaning I free the memory. So anybody can use it. Maybe the program starts to run and then somebody else occupies that. And this might be a problem because we were lucky this time and we had free memory, free contiguous memory. So we could allocate an array. Then we got, for example, just imagine we keep filling up the array. 10. Now what happens? We don't have any more contiguous memory to allocate to grow our array. So this is gonna fail. If we want to add new memory, new data to our array, we cannot, because we cannot allocate more contiguous memory to our array, and this is a problem. The program might fail probably if it cannot find some area of memory for our array. So why linked lists might be useful in these cases? Because linked lists are, as we were seeing before, they don't need contiguous area of memory, because the elements store the a pointer to the area of memory of the next element, so we can move around. For example, imagine that this is our first the head of our linked list. That's okay. Then we add a new element. Where is this going to be allocated? It might happen here, but it also might happen. Now we add another one. It might happen here. We add another one. Might happen here. So you see that also they don't have a fixed size. So this is really useful because we don't have to grow the size each time we reach a certain point of elements, a certain number of elements. We can just keep growing and growing as much and fill as much memory as we want. Let's not do that maybe, but it's feasible. We can keep, for example, we can keep growing our array, our linked list as much as we want. And the contiguous area of memory is not an issue. Obviously, I'm showing an example here. So a square is not exactly an area of memory. They occupy obviously a bit more memory than a simple array. As you can see, we're storing in a single element, we're storing both an integer and a pointer. An array will just store in an area of memory will just store an integer, and the next one another integer and another integer. The element instead stores an integer and an element pointer, so that takes more memory. It's just a matter of really deciding what we actually need. That's really all that matters in these cases. For example, even in this case, we, for example, started storing the current size. This occupies memory too in our linked list. We might have a system that has ton of computing power but not much memory. So we might decide to not store the current size, but we can actually I can show you. Let's comment out the current size. We don't need this. Let's comment out the decrement of the current size, and the current size increment when pushing. Then here we have a problem. What do we do to get our size? We might actually do something like this size. No, maybe let's call it length for now. Not exactly a length, but and in the end we're gonna return it. But we could do this while head is not a null pointer. It's basically the same idea that we had for the reverse and the how do you call it? The instructor. Maybe let me increment maybe this size a bit. Maybe this is a bit better. Didn't think about it earlier, sorry. But yeah, this is the head. We're gonna go to the list of elements, and each time that we hit the loop, we increment it. So we could also need another thing that I didn't think about. Need to track the current one. So the current is going to be the head, and the current now becomes the current next. This might be something else that we could do. It's not really much more efficient. It's not really more efficient memory-wise, since we're gonna allocate what else in like language. Oh, I made a typo here. I was saying this is really not that efficient, because in the end you're still gonna occupy a ton of memory, because you need to store the length in any case each time you want to calculate the size. You gotta keep track of the current, so you gotta allocate some memory to at least to store a pointer to the head. So this is really not that efficient. For example, you could omit the current size really if you don't need it, and if you really starved for memory. So let's go back to our previous solution. That is really good in any case. We still have some minutes. We could go maybe. We could do have fun a bit with doubly linked lists, or we could try maybe. We could maybe try smart pointers. To be fair, I don't remember much about smart pointers, so I'm probably gonna do some messy stuff. Let me think. We could maybe change the. Yeah, let's try this. This is gonna be a bit different. We're gonna store in our element another element too. That is the previous one. What does this mean? This means that each element will keep track of the next element in the list and the previous one. This makes it a bit easier to do some stuff, but consume obviously a bit more memory, since we need to store another pointer for each element. So let's go through it. Okay. So obviously the head will have no previous element. So it's gonna be not pointer in any case, but and the last point, the last element it's gonna have no next. So let's see. Let's go through. The current size is gonna be untouched. Doesn't really change anything. This one also won't change anything. But this, okay, this is gonna be a bit different. Say we're adding a new element. We create it. The element next points to head, and that's correct. The current head, so rev at least, is gonna point to element, and then we switch them around. The head becomes the element. This should be it, right? Element next is the head, because we push the, yeah, that's correct. We push to the top of the list, to the first element. And this seems a bit counterintuitive, saying add, setting the element to the head like this, but this is much simpler than it uses less memory for sure, because we don't move much things around. Otherwise we could store a head in a prev element, and maybe it could be a bit clearer to understand, but really this is the simplest solution. Then we gotta do the same for pop. We're gonna go through this. Okay, the head comes the element next. Okay. Yes. Take the data from element. We gotta change the element prev. It's gonna be a null pointer. Why is this important? If we don't do this, when we try to access the element prev of certain elements, we might try to access some memory that it might be allocated, or maybe it has been deleted. No, actually it has been deleted because we deleted the actually here before popping it. So that's important. I'm gonna do it. Oh no, wait, I'm making a mistake here. We pop in the element. We should change the, oh yeah, it's my mistake. Because we're not changing the previous of element, the previous of head. Because the head must always point to a null pointer previously, because there's nothing else to it. So let's go. Oh, this is gonna be the fun part. The reverse, because since we're gonna change the pointers to the next, we're gonna change also the previous one. This is gonna be a bit more complicated for our reverse. Let's see. We keep track of the current. Current becomes head. Head becomes head next. Current next becomes step. So we gotta do, okay, what we need to change here is add prev. Instead of becoming a null pointer, becomes current. If I'm not mistaken. Yes. Because add next, let me think a bit. current is the head. Then head becomes the next one. So yeah, this is correct. Because current was the previous head. Yeah, this is good. And current next becomes temp. So current prev should be, I'm getting confused here. Oh gosh. Current next is temp. It was current. So current prev should be head. No, it cannot be head. Because prev, the previous should it be temp? No, it shouldn't be temp. So current head next points to next points to temp. Okay. Okay, let's think a bit. We have position 1. We're at the head. We start. It's not a corner pointer. Okay. Current one is a pointer. We save it. Then the current becomes the head. Okay. Then the head becomes the next one. Okay, so now current is here and head is here. The head prev becomes current correctly. The next we're reversing here. This is important. Let's not get confused. Let's go through again. Head, current, no. Current, head. Head, prev becomes current. Nope, becomes head next. Becomes head next, because we're reversing here. So this was wrong. This is not correct. No, wait. This is even worse than what I've written. Complicated my life, really. This should be current. I gotta look it up. I complicated my life. But you're right. I wrote current before. The current one, the head prev points to the head becomes the head next. Okay. So this is the head here. Current is currently in the previous head. So current no, you see, this is what I'm getting wrong. Current prev becomes the head. Oops. I'm still missing what head prep is. Maybe I don't actually need to do that. Still missing some. No, wait. Like this. This is it, if I'm not mistaken. Let's try and run tests. Haha. Oh, I mean the semicolon. One test failing. You see, there is a segfault. I'm accessing memory that I shouldn't. Yeah, I'm probably making some mistakes here. The head becomes the head next, and that's correct. How was it before? Let's go back to the previous version. Okay, this is the previous version. The current result becomes the head. The head becomes the head next. So probably it should be just next equals head prep. I need another temp here to do that. If head becomes head next, then head next. Oh no, because this head is not this same one. It's current. So head prev. Getting confused. Let's do it like this. This might confuse me a bit less maybe. So the head is now current next. So current prev must be head. That's the only valid thing. The current next becomes head, then the head becomes previous next. Temp was current becomes, yeah, this seems correct now. Let's try and run them again. Still a segfold. What am I doing here? Pop from size 1. Oh no, wait, it's another thing that's failing. We have a failure here? Which test it is? Pop from size 1. Let me see. Pop. It's from size 1. There it is. Oh, it pushes one. That's correct. And then it pops after it equals from the side. What's wrong here? Maybe the structure is doing something. I don't expect the structure to break something. Yeah, the logic is identical. We just go through the old list and allocate when necessary. This should be correct because the head is an up point. That's correct. We allocate a new element. This head. So I'm making some mistakes here. Oh, that must be it. Take the element. Element X next becomes the head, and head prev becomes the null pointer. Yes. Or is it? I think I need to do this. I think this is the issue, maybe. This is gonna probably fail some other place. No, it's not gonna fail. So this line here is the problem. This is at least causing the problem. It's not the actual problem. Probably I need to, let's see, this is the element data. I think I just need to move this after we delete the element. Because if we assign the previous to null pointer, it becomes, no, still getting the error. Why is this happening though? Let me think. The current element is add. Okay. Element X becomes the head, as expected. The previous head, the head previous becomes a pointer. That's correct. Oh, that's the issue. I didn't take into account the fact that if it's only a size one list when I access the previous from add here, this is a null pointer. And that's why it's failing. So I should check here if add not a null pointer. And only then actually assign the previous one. This is important. If we don't do this check, we'd have a previous element still allocated here. Element will still live here. Let's say we actually would have add pointer to a previously deleted element. So it's good to do this. It's safer. And that's it. We created our doubly linked list. We had some issues with the reverse. You need to wrap your head around a bit the swapping of elements, since you're changing more pointers around, but we did it. Nice. And yeah, as I said, a doubly linked list would have complicated stuff, and it did. As we can see, we have some more logic to handle the previous element being non-existing here, for example. The swapping becomes more complicated. The structure doesn't change at all, because we're just gonna go through the list and delete all the memory. So we don't care whether an element for a moment points to a deleted area of memory or not. So at this point, we're gonna have an add that has a prev element that points to a deallocated area of memory. That's not exactly safe. It would be safer to point the prev to a null pointer. But that's not necessary, really. With destructuring, with the allocating memory, we don't need that. It complicates the structure for no need, really. It might be safer if somebody comes and edits our code and adds some more functionality here, but that's not gonna happen. maybe who knows. It's gonna be a funny bug to handle, I guess. And also the push, it's a bit more complicated, but not that much. It's just that the new element that we create is pointed also from the previous head, just a line more. And that's it, I guess. We stream. Oh, it's 1 hour precise. I think we can wrap this up. It's been fun. I hope I'll do some other stuff in the future. We'll see. I hope everybody enjoyed it. I didn't see many people writing in chat, but that's fine, I guess. I want to leave some time for questions, but I'm not sure whether there is somebody watching. So I'll just wait a bit. I guess there's nobody. This has been fun, in any case. I hope everybody enjoyed it again. Maybe next time we can go through this whole exercise again, but using smart pointers. Smart pointers are really easier to handle. It makes code safer, actually. They're not that easy to handle, but for example, you see this delete element and this deallocator. We wouldn't need any of this stuff because the smart pointers will take care of that automatically. I suggest you look up if you want to explore a bit more creating a solution similar to this, but easier to handle for the memory with smart pointers. I suggest you look up unique pointers. We'd use that in this case. For example, going here, this would become, since this is, since here we're using a double linked list, let's go back to, let's assume we have a single linked list. Since a doubly linked list makes handling smart pointers a bit harder, really, because some pointers are shared. For example, the head pointer is shared, and you cannot share unique pointers. As a matter of fact, they're unique. That's why they're so useful. And I was saying this would be this element here would become a smart pointer, a unique pointer, and this one the same. And the cool thing about smart unique pointers is that they're automatically deallocated and they're memory freed when they go out of scope. So let's say here pop. We pop an element. Where is it? Here, yeah. We assign the new head to element next. The only pointer that's called it, the only variable that's pointing to the area of memory that previously was the head is element. So this element is gonna go out of scope after the pop function finishes execution. So it will be automatically deallocated, and that makes memory. In this case, it might be a bit of overkill since we're just allocating, building a really small linked list, but it can give you an idea on how simpler can be handling memory in C++ with the smart pointers. And it's the point is that, pardon the pun, the point is that it's much safer. Because when you go back to the code and maybe edit it for some reason, maybe to make it a doubly linked list, you find out right away that there are some things that you gotta handle with the memory that might not come out when using raw pointers, since they let you handle memory in a manner that is a bit more low level, let's say. They have some smaller overrides, the smart pointers, but that's okay, really. For the benefits they bring, they're useful. Maybe we could even in the future work a bit with the copy and move constructors and operator. These are, we could have done it at this actually. Basically, the copy, as the name implies, copies the list to a new area of memory, bringing with it all the elements and duplicating them. The move instead moves the area, the list. So the previous one becomes unusable. You could try and use it, but things might go wrong. Oh, also something that I didn't point here earlier. You see that all the functions except this one are marked as non-const. The size is the only const one. What does this mean? This means that this is a way to avoid modifying the object that calls the size. What this implies? This implies that size, whenever it's called, is never gonna change the object. So I can call size tons of times, but it's never gonna change the add or the current size value. Never. That's what const mean. This tells the user of this list that calling size will have no side effects on the object. Push, pop, and reverse obviously have some side effects, since they must have some side effects. We could try, and this is const is part of the signature of the method. So, for example, if here we define a size const, we cannot remove it from the implementation. If I run this, it will fail. The compilation actually will fail. Yeah, you see. Error no declaration matches size the simple linked list size, because it cannot find an implementation for this method here, because we declaring another one. And for example, we could also try do a thing as an experiment. We can declare this const, the push, also here. See what happens. Bam. This fails. And this is important because it prevents you from making mistakes when writing code. If you first define the interface of your class in a clear manner, in this case, our list had 4 methods. It was clear that the size will return only the size of the list and wouldn't modify the object at all. So we declare the const. Push would obviously modify the object since it adds an element. So it couldn't be const. Pop, same, and the rest same. They do modify the object. But for example, if we had defined push as const and then implemented const, the push, the const version of push here, like we just did, we couldn't do this stuff here. Neither this, neither this. This would fail, and in fact it does. The message is not exactly clear, but it tells you error assignment of member simple linked list add in read-only object. yeah, this is a clear way of looking at it. The const makes the object that you're modifying here read-only. So since this modifies a list, I didn't do this, but this is implied. Basically, every time I refer the add and current size in the method of list, it's clear to the compiler that I'm referring to this add and this current size. Because the here for all add and I could have done this each time really, but that's just more code to write that we can avoid writing. So it's just clear to do this. They're not defined in any other way, so it's clear that they're referring to the members of the class. Sometimes some people like to define member classes like this, member of the class like this. So it's clear you refer them like this. So it's clear at first sight that they're members of the object that you're modifying. It might be useful when you're dealing with huge code bases, but we like to keep it simple now. Let's revert our changes. We run the test again, and we can see that the push now works. Oh no, what I've done? What's going on? Oh yeah, I removed the prev from our doubly linked list element. That's it. I guess we can wrap it up. It's been fun again, and that's it. I was Silvano Cerza. I guess we can see each other next time.